Hi, today we're going to be talking about tessellations, or tessel what? So first, a tessellation, what is it? It's a way to cover a surface with flat shapes so that there are no gaps or spaces in the pattern. So this is what we see over here on the left side of the screen. The top we see triangles that are connected together, and the bottom you see a mixture of triangles and squares connected together to cover that space. There's no gaps, there's no overlap, um, and that's what we're looking for in a tessellation. So there's four kinds of tessellations that we're going to talk about. We have regular, semi-regular, K-uniform, and non-regular. All right, we're going to start with the regular. There's three rules that a regular tessellation has to meet. The first rule is that the pattern has to cover that infinite space, just like the definition says. There can't be any gaps or overlapping in it. The pattern must consist of regular polygons. So you can't have like irregular polygons or anything like that. It must be a regular polygon. And each vertex has to look the same. Right? And this is actually going to help us name the tessellation or the tiling. So that is very important. There are three kinds of regular tessellations, one using triangles, one using squares, and one using hexagons, which is what you see here. Now, one thing I want you to notice and pay attention to is the vertices and the sum of the angles at each vertex. So, for example, look at the squares first. All right, we know that a square has four right angles, right? Four 90-degree angles. So at each vertex where the four squares meet, we add up those four right angles at that vertex, you get a sum of 360 degrees. And that's important. If you look down at the triangles, again, equilateral triangles, we know that those have each interior angle is 60 degrees. And here at each vertex, you have six triangles that meet to create that vertex. So six triangles, each of those triangles has an angle of 60 degrees at the vertex. So you add those up, and again, you get the 360 degrees. We look at the hexagons. All right, the hexagons, a six-sided shape, right? Each interior angle is 120 degrees. All right, three hexagons meet to create a vertex. So 120 degrees times three, that gives you the same 360. So we see this pattern here that for a regular tessellation, the angles at the vertex must add up to 360 degrees, which makes sense because if it doesn't, then we're going to have either spaces or overlap. We'll have a space if it's less than 360, or we'll have an overlap if it's more than 360. So that's really important. So what I want you to do is think about a pentagon. Right? Why does a pentagon not work? And think about the interior angles, and if you were to match those up, why would a pentagon not work? And what about an octagon? What would happen if we tried to use an octagon? Right, and that's going to be in the homework as well to address those. All right, next is a semi-regular tessellation. All right, a semi-regular tessellation is made up of two or more regular polygons. All right, so it's kind of similar to the regular, but instead of just being made up of one shape, it's made up of two or more. The same rules apply to the semi-regular tessellation as to the regular tessellation. And again, each vertex must have the same arrangement. If it doesn't, then we can't name it because the vertex would be different, and how we know what we're talking about. So we name the tessellation or the tiling by the number of edges of each shape represented at the vertex. Right. So if we look at this top left one, we have the blue hexagons and then the red and green triangles. So if you notice here, you can pick any vertex, and you notice that it's got four triangles and a hexagon. All right. So we want to name the vertex in such a way that the smallest numbers go first. All right, so we don't want to name it 6333 or 33633. We want to put the smallest numbers first if at all possible. So this one is actually going to be called a 3, 3, 3, 3, 6 because there's 3 triangles and a hexagon that make up that vertex. Move over to the right. This one is also made up of hexagons, triangles, and squares this time. So if you pick a vertex, you see that it's going to have the triangle, the square, a hexagon, and another square. And that's where that 3, 4, 6, 4 comes from. All right, you can pick any one of those vertices, and it's going to be the same 3, 4, 6, 4 pattern. Lastly, at the bottom, we've got hexagons and triangles here. All right, we see that in this case, if we pick any vertex and we start again with the smaller sided shapes, we're going to follow this 3, 6, 3, 6 pattern. Right, those meet to create that vertex, and it's the same at every vertices, and that's what makes it semi-regular. Right here, I did these enumerations by hand and took the pictures of them. I used the foam pieces. I have provided a PDF for you to print off, and you can do these as well, so you can see what we're talking about. All right, but this is the same 3 regular tessellations that we talked about earlier, the triangle, the square, and the hexagon. All right, there's also, I did the enumeration for the uniform tessellations as well. Okay, so there's 8 ways to construct a uniform or a semi-regular tessellation. And so there's 4 on this slide and then 4 on the next. So with this first one, what we're looking at is you can pick any of those vertices, and you see that it follows this 3, 3, 4, 3, 4 pattern. And that's how you would name that vertex. And remember, it has to be the same at each vertex in order for us to be able to name it. All right, with the next one, we see we've got 3 triangles and a square that make up each vertex. So we name that one 3, 3, 3, 4, 4. All right, again, you want to name them in such a way that you're naming around a vertex and you're naming from least to greatest if at all possible. The next one is really interesting. We have this, what we call it the 3, 12, 12. We got the dodecagon and the triangle. And if you notice, the reason we don't call it a 3, 12, 3, 12 is that those triangles don't actually meet to form a vertex. The vertex is actually formed by the 2 dodecagons and the top of the triangle, or one of the sides of the triangle. So we actually name that a 3, 12, 12. Right, and then lastly over here we have the hexagon and the square and triangle. So we named this a 3, 4, 6, 4 because those are the shapes that make up that vertex, and we kind of saw that earlier as well. All right, the next 4 here we have the 3, 6, 3, 6 first. All right, again, this is one we already talked about. The difference between this one and the 3, 12, 12 is that you see that the triangles do actually meet to create part of that vertex. Whereas before, the side of the dodecagon split them up, the hexagon does not do that. So we have this vertex that's actually, that allows those triangles to meet. Next, we have the 4, 6, 6, which includes the square and the hexagons. All right, so you see that at each vertex, you have the square, the 4, and then the 6 and the 6. Pretty self-explanatory there. And then next, the one we have is the 3, 3, 3, 3, 6, which again is one that we already looked at. And if you look carefully, you will see that I did mess up on this one. It's not exactly a 3, 3, 3, 3, 6, but I recognize that. And if you can point out where I went wrong, that's bonus points. So include that on your homework as well. Lastly, we have the 4, 6, 12. You have the square, the hexagon, and the dodecagon. You pick any vertex there, and you will see that it follows that 4, 6, 12 pattern everywhere. All right, so looking at these, all right, would these work for a uniform tiling? In other words, would this work so that if you were to add on to these, would every vertex look the same? All right, the answer here is no. If you take a look at that first one, the 3, 7, 42, the 3 is that orange triangle. You see it better in these other examples, but it's that tiny orange triangle there. And And if we were to try to add on to that other side of the triangle, what would we add on? Right? Because remember, it would have to match that vertex of the 3, 7, 42 that we see there, and there's nothing that we can add on there that would actually work. If you tried to add on a septagon, then what would you add on to the other side of it? It would have to be the 42 gon, and it wouldn't fit there. And that's the case for all of these. And essentially, what's happening here is that if you have an odd-sided polygon, in order to create a uniform tiling, it would have to be the same on all sides. And if it's not, it would have to alternate. But with an odd-sided figure, if it alternates, that's still not going to work because you're going to end up with an odd side. So that's one thing to consider as well. So these actually do not work for a uniform or regular, semi-regular tiling. All right, now what about these? These look a little bit better. They look like they might actually work. But if you notice, again, if you were to look to add on to these, you know, what would you put on the other side to create a vertex that's the same at everywhere, right? The same arrangement at every vertex. The thing is that we can't. If we do, we're going to get overlap, we're going to get gaps. It just isn't going to work. But we can still add those same shapes and create this pattern, but what that's going to do is actually create a second vertex. All right, and this is where we get into the K uniform tiling. All right, this is, again, edge-to-edge tiling, same as before, but you have what we call K distinct transitivity classes of vertices, basically distinct vertices. All right, so like a 2 uniform tiling is going to have 2 distinct vertices. We label these A and B, and you can see those over here. I did the best with the arrows that I could, but that's what those are for. We can name those vertices, which is what I've done. Same thing with the 3 uniform tiling. All right, make sure that you pause the video at this point and make sure that you actually understand that and see where those numbers came from. If you have any questions, let me know, but there's some problems like this in the homework as well. So if we go back to those examples from before, what we see is that we can still create these tilings, but we have 2 distinct vertices that are created. All right, so we would combine the 3, 3, 4, 12 with a 3, 3, 3, 3, 3, 3 in order to get the vertex that the 2 different vertices to create this tiling. And it's a very unique, very creative tiling, and that goes for all of these. And there's a bunch of these. You'll see in my references that there's links to plenty of these. The Wikipedia page for this is pretty incredible, and that's actually where I got these pictures. But this is where we see that those vertices turned into a 2 uniform tiling. All right, this is actually an enumeration chart. So I actually did the first 11, which is what you saw earlier, the 3 regular and then the 8 semi-regular. As you see, there's still a lot of room for learning. All those question marks, we don't know how many of those exist yet. So there's still plenty to learn about these things. But this is just really neat because this is what we know already. So again, that's more to explore and check out later. Lastly, we're going to talk about non-regular tessellations. This is using irregular polygons or weird shapes. I think this one with the dogs is pretty interesting. But you see, these are just more fun. You know, there's a lot more that goes into them. We're not going to spend a lot of time on those, but they are pretty neat. Just for fun. Lastly, we're going to talk about the Kepler tilings very briefly. Kepler dabbled in some tessellations. He even wrote a book on them. But what he did is he actually fused decagons and he called them monsters, which is what you see here. And he talks about that in his book. And so that's pretty neat and definitely worth exploring further, but just not right now. But still really cool. And then there's my references. That first one has a lot of great examples of different tilings, and the Wikipedia on Euclidean tilings is really good as well. So I hope you enjoyed this video, and I look forward to your feedback. Thanks.